Okay, so probably a good time for me to start, I would think, it being about 1 minute past the hour. So I'm gonna take it away. Make sure I can remember how to do this. I think I need to make this viewer full bright. Give me a second to make that happen. So let's talk about Pi Day a little bit. March 14th, that was yesterday, 314. And I'm sure a lot of presentations that have been given about Pi Day have been more geared towards pi, the irrational number. But the pi is used for a lot of other things too. Chemists have a view of pi, particularly of pi bonding. So I'm going to kind of take you through some real basic organic chemistry today, and maybe show you some applications and the like. So let's see, moving along. There we go. So, question is, what is a pi bond? And I thought I would put this slide right up here, right up at the beginning. I even have models. They're back here. Let me get them. Edit, and then we will move this guy. Hey. Okay. All right. So on the right-hand side is a representation of ethylene or ethene. It's 2 carbons, 4 hydrogens. The molecule is flat. All of the atoms are in a plane, and each of those kind of dark cylinders that connect the balls that represent atoms are bonds. And we think of those bonds as being the localized sharing of 2 electrons. So there's like 2 electrons that kind of hang out in those areas that cause the nuclei that they're attached to just attract each other. Okay? So basically, they are the little springs that are holding the structure together. Okay, so I haven't accounted in the model on the right. I haven't accounted for all the electrons. There are another pair of electrons that live in a space above and below the molecule, and these are very accessible. When you have electrons between 2 atoms, they tend not to be very accessible. Other atoms have a hard time kind of getting in there. They're kind of hard to access. These this pi bond, as it's called, I'm not giving anything away. This pi bond, the blue and the red-looking beam areas, it represents electrons that can be accessed by other molecules from the outside world. They do contribute to attractive forces between the atoms, but instead of joining the atoms in like a headlong sense, like along the axis that joins the 2 atoms, they're off above and below. Okay, so that's basically what a pi bond is. You may ask, well, why are there colors here? So I'm not going to get into the math or anything, and pi does show up in the math, of course, but the colors represent phases, and I'll talk a little bit about phase a little bit later on. It's basically where, if you have adjacent blobs of red and blue blobs add together and red blobs add together, but red and blue would cancel each other out. Okay, so let me get that out of the way. All right, because I'm sure Dolly and Phil don't really want that in their way for the whole talk. And then we're back to the slides. All righty. All right. Thank you all for your patience with me as I move things around. Right. And you will see pictures of gratuitous pictures of cats. Let's see, on the left is Thor on the right is Loki, and they are my youngest two. But yeah, they're about 5 years old now. Well, 4 years old now. Let's see. Moving on with the talk. Okay, so I'm going to kind of talk to you about how to put molecules together right now. This is a picture of the main group. You'll notice, let's see, over here, I've got lithium and beryllium, elements 3 and 4. Then it goes to 5, 6, 7, 8, 9, and 10. Okay, the next row is actually, 11 through 18 uninterrupted. And then in this next row down here, I've got calcium and gallium. And what I've done is snipped out the transition metals, because those do other things that we're not talking about today. But this little square here with hydrogen and helium on the top represents what's called the main group of elements. And a lot of the times what we do is figure out how many electrons are available for chemistry for an atom. It's very easy. You just count how many columns it is from the left of the periodic table, right? So fluorine there, where I've got my laser pointer, is 1, 2, 3, 4, 5, 6. It's in the 7th column from the left, and so it's got 7 electrons to play with. Lithium, a neutral lithium atom, only has 1 electron to play with. Okay? The magic number is 8. If you're helium, neon, argon, krypton, you've got 8 electrons, and they kind of fill up the outermost regions of the atom and protect it from actual chemistry. Right? And as a chemist, I find this highly offensive. But they don't do very much. Right? That was a joke. Okay, so some elements like fluorine will outright just take another electron away from something else, and it'll be F minus when that happens, because electrons have negative charge, and then it'll have 8 electrons, just like neon, and it'll be happy. Okay? Chlorine can do the same thing, so chlorine turns into chloride, Cl turns into Cl minus by picking up 1 electron. Cl in that case becomes like argon. Kind of in the middle here, instead of just picking up electrons, elements like carbon, nitrogen, and oxygen very commonly share electron. The point is we're trying to get to 8. Let me go to our next slide here. And, basically in the second row, that's all I'm going to talk about today. There are strict limits on electron counting. I have a periodic table behind my screen if you want to look at the periodic table for reference. So what I'm talking about right now is a thing called Lewis structures. We need 8 electrons for the maximally stable structures, right? 6 electrons in special cases, yes. Boron is a special case, but I'm not going to talk about much about boron today. It's got lovely chemistry, but I'm not going to talk about much about boron today. So 8 is going to be our goal for today. And these 8 electrons have like 4 slots that they can be in. There's only like 4 places to stash electrons, either in bonds, which we talked about. They are the pairs of electrons represented by lines that are basically shared between 2 atoms, and the positive charges of the nuclei of the atoms are attracted to the electrons, and the whole thing kind of stays stuck together. But we can also have things called lone pairs, where it's a pair of electrons that an atom just keeps to itself. Right? Like Gollum, it's with the 1 ring, right? It's the precious. So all of this means that there's really only a limited number of structures that you can have around an atom. You can have linear arrangements of electrons, or trigonal, planar, right? So that's basically atom in the middle with like maybe 3 areas of electron density coming out. um, basically at 120 degrees from each other, or tetrahedral. Okay, so here's a molecule, methane, methane, utarzan, methane. Yeah, um, my students don't laugh at that joke either. So carbon is 4 from the left of the periodic table. So let me bring a table forward here. And maybe just move it up so it can be seen if people want to see it. So carbon is element number 6, but if you count columns and ignore the transition elements, it's 4th from the left of the periodic table. Hydrogen, well, hydrogen is in the first column. Hydrogen only has 1 electron. There are 4 hydrogens. That means there's 4 electrons. We have 8 total electrons to play with for this, right? So if we're going to try to pretend to make structures that we understand to be stable, first of all, we have to attach the atoms together. So here we're going to attach all the hydrogens to carbons using pairs of electrons represented by lines. So we have a carbon in the middle, and we just put 4 hydrogens around it, because that's what's in the formula, and connect each by a line. Each line represents 2 electrons, 4 lines, 8 electrons, we're done. Yay. So this representation can also be used to predict structure. If you have central atom with 4 lines coming out, it's going to be at the center of a tetrahedron, especially for these main group elements. Right? So far, so good. I got a few more examples for you. I might not go in detail through all of these examples. I sent Stephen a PDF of this talk, so if you want this stuff, then we can get you PDFs. Nitrogen is much the same story as methane was. Nitrogen is 1 column to the right of carbon, so it's got 5 electrons. But then you've only got 3 hydrogens, so the 3 hydrogens each have 1 electron, so your total is 8. Again, just like methane was. But when you attach the 3 hydrogens to the nitrogen, you only use up 6 electrons, and then you've got another 2. So you give the nitrogen a lone pair, as it were. You just give them possession to the nitrogen. Why nitrogen? Well, the hydrogens are happy just with 2 electrons in. Right? Hydrogens don't really want a 3rd electron, or the hydrogens do not want 8 electrons. That's the last thing in the world. So the nitrogen is very happy to accept having another pair of electrons. And if you think about it, the nitrogen now has access to those 2 electrons, plus the other 6 in the bonds. It has access to 8 electrons. It's happy. And the structure that would be associated with that. The nitrogen is still in the center of a tetrahedron of electron density. It's basically got 3 bonds pointing down. And then there's the lone pair, which is invisible in the way we usually represent molecules, but it still has an effect on the structure. It bends the hydrogens down, so you get what's called a pyramidal structure. It's not flat. So far, so good. I always have a little bit of trouble keeping an eye on the nearby chat. I did the same with water, H2O, and here I won't go through the whole thing, but in the final stage, we have an oxygen atom. It's connected to 2 hydrogen atoms. That's using up 4 electrons. The other 4 electrons are just given to the oxygen as 2 lone pairs. And, oxygen is still in the center of a tetrahedron of electron density. It's just that 2 of the lone pairs would be invisible to us. And we would have a bent looking structure. And so you can make predictions about structures from how the electrons are being shared. So far, I haven't really talked about anything that involves pi bonding yet, though. Pi bonding does show up in here. Let's talk about carbon dioxide. Carbon dioxide, our favorite villain gas of the age, for its role in climate change. So carbon's a bit more complicated than what I've talked about so far. Carbon has 4 electrons, because it's, we've talked about that before. Oxygen is 6 from the left of the periodic table, not counting the transition elements. So 2 oxygens is 12 electrons plus 4 gives us a total of 16 to play with. Our first stage, and I'm following rules. These are always the same rules over and over again. If you can play Monopoly, you can certainly make Lewis structures and predict the structures of molecules. So what we have to start with is attaching everything with at least a pair of electrons to each other. So my top structure has the oxygens attached to the carbon with single bonds. I have now used 4 electrons of those 16. Then what we do is figure out who to give the rest of the electrons to. There's a thing called electronegativity. It's a measure of the strength of, or it's a measure of how atoms attract electrons in bonds to themselves, right? Oxygen is pulls at electrons in bonds more powerfully than carbon does. The trend in electronegativity is it increases the more you go to the left of the periodic table, and it increases the more you go up in the periodic table. So we give we basically make sure that the oxygens have their 8 electrons. I gave them each 6 electrons in lone pairs, and they have access to another pair of electrons in the bond. So that's 8 electrons there. Well, let's see. Now that's all of our 16 electrons used up, so carbon's not happy at this point. So what we do is we use these curvy arrows to represent how electrons are going to move or be shared. This carbon, even though it's not as electronegative as oxygen, doesn't have an octet, and that's just not acceptable. So we'll force an oxygen to share in a sideways manner, in a pi bond, a pair of electrons. Right? So basically, this ends up being the structure of carbon dioxide down at the bottom here, where you've got a double bond to each of the oxygens. Okay, double bond is 4 electrons. Each oxygen has another 4 electrons. Each oxygen is still happy. The carbon has 2 double bonds, a total of 8 electrons. It's happy. Done. Okay. Tag, the arrow is more of a conceptual shift when you're talking about moving electrons in this stage. Later on in my talk, I'll actually use the arrow to indicate what pair of electrons on one molecule is going to attack what space in another molecule. All right, moving on, and yeah, how those areas of electron density show up in space is kind of interesting. The double bonds end up being perpendicular to each other. So the OC on the left would be in the plane of the slide. The CO on the right, that pi bond would be coming out at you, and it's basically at 90 degrees to the slide. Okay, and I have some representations of those things. Let's see. Yeah. Well, yeah, these lobes are actually telling you more about the probability of finding an electron. A lot of times in the drawing programs, they give us really skinny lobes, but honestly, they are quite fat, as you saw in the ethylene model that I had made earlier. Actually had made that using calculation programs, so it's fairly accurate. Here's another example. I'm doing a lot of examples because the basics are important. This is Marduk. She is Quite the kitty. We'll tell you more stories later. NO2 minus is an example of a molecule. If you go through all the steps, you get to a point where the oxygens have their octets, the nitrogen has only 6 electrons, and then you have to say, okay, I'm going to force one of the oxygens to share. So in what I've drawn, it was the oxygen on the left that I forced to share. We put a NO double bond in there. Then everything had its 8 electrons. But there is really no reason to have chosen the oxygen on the left. I could have equally chosen the oxygen on the right. So what gives? Well, the problem here is that these Lewis structures over-represent the localization of electrons, right? The lines are great. You know, but sigma bond, a bond between an N and an O that is like between the two atoms. That's a pretty good representation usually of the localization of those two electrons. But pi bonds tend to kind of slide around a little more. So I think my next slide makes that a bit more clear. N. So yeah, so basically, how do you decide how do you decide which oxygen atom to make share? Why not both? We call this resonance. And in fact, the true structure of NO2 minus, this is nitrite, occurs naturally in bacon, by the way. It helps make the bacon a bit carcinogenic. I love bacon. So it's not bothering me, but yeah. The bonds in between the N and the O, you shouldn't really think of them as single or double. They're somewhere in between, right? Both of these structures contribute equally to what's called the resonance hybrid. It's basically, we have to kind of consider both of these at the same time to really think of where these electrons are. Okay. Okay, and so resonance, this idea that we can move electrons, it's a patch on the theory. The double-headed arrow like this is supposed to indicate that we're just moving electrons around. We're not moving, or we're just moving the representation of the electrons around. We're not moving any of the atoms, and that both of these contribute some way into the actual electronic structure. This stuff is actually so useful that we continue to use it, even though we have more accurate methods of figuring out where electron density is. All of these models that have all of the blue and red lobes on them are more accurate models of electron density distribution than what I've just shown you. But they're hard to use, they're hard to figure out. So we love these. As chemists, we love these depictions of pi bonds. Okay, and so we're halfway to orgo because we've got double bonds. A lot of the chemistry of orgo is double bonds. Here's Loki trying to look wise at us. I'm going to introduce a little bit of the drawing jargon. So this is a molecule, it's benzene. It's got 6 carbons in a ring. Each carbon has a hydrogen, and it has a single bond to one carbon and a double bond to another carbon. We will often represent it in the manner shown on the right. Each vertex represents a carbon atom. Each carbon atom is assumed to have 4 bonds. If the bonds aren't explicitly shown, they are two hydrogens. Okay, so anytime you see like this particular carbon I've got the pointer on, it's got a double bond and a single bond. That's 3 lines. There'll be a 4th line to a hydrogen that represents that. Okay. Here's another molecule. What is that? That would be a 3-methyl 2-pentene. Doesn't matter what the name is. but it's got 1, 2, 3, 4, 5 carbons in the chain and one dangling off. 1, 2, 3, 4, 5, and then the guy dangling off. I've represented all the single bonds, and then you can see the double. Anything, lines that aren't shown, they are two hydrogens. So far, so good. And Phil, you are right. The single bonds and double bonds in benzene are smeared around. We can represent that. We can represent that with our resonance structures, where we can say, hey, why don't we use a curly arrow to move one bond, and that will necessarily mean that we have to move the next bond and the next bond, otherwise we'll have like 5 lines to carbons, and that gets people very upset. I actually showed some real advanced stuff where there were 5 lines to carbon drawn once. Each line was not representing 2 electrons at that point, but I did have a student start crying. So just a 4th-year student, and she had invested her life in organic chemistry, and I'd blown her mind. Yeah. The depiction of these resonance structures, these are called the Kekulé structures, because I think it was like 1860s, I don't know, 1860s or so, when this conception of benzene came about. And Kekulé actually came up with this idea, and basically he said that it came to him in a dream. And that's one of my favorite stories about chemistry. A more accurate depiction is, basically you've got, it's shown on this left-hand side. And let me move the actual model forward so you can see it. It's a bit small. Sorry. Okay, but I made a 3D model using molecular orbital calculations. If you zoom in on it, you can see the lowest one, the lowest little thing that looks like a hamburger. It's got a pair of electrons in it, represents where a pair of electrons can go. And you can see that that pair of electrons is really smeared out amongst all 6 of the carbon atoms. And then if you go up one layer, you can kind of see each structure there has 4 lobes, 2 red, 2 blue, that kind of encompass half the molecule. And it's almost the same picture, except it's, one is oriented along like the y-axis, and one is oriented along the right. And these would represent another 2 electrons each. So the bottom 3 structures would be where 6 electrons are hidden, or where 6 electrons are present. And they represent the double bonds. These structures up top, the 3 structures up top, are called antibonding orbitals. They're vacant. And I'm not really talking about antibonding orbitals too much today. I really do like the one at the very top. I was a little bit surprised when the calculation came out, and it kind of looked like this weird crown sort of thing, but it actually makes sense. If you actually gave benzene more electrons, they'd have to go in these upper orbitals, or these upper structures, and that would destabilize the benzene. I do like the hamburger bond. Okay, let me move that out of the way. Edit. Let's see, what's the time? I think we're making okay time here. And pop you over there. Okay. Okay, so some properties of the single bonds versus the double bonds. You can rotate around single bonds. They're basically just like they're just basically like I don't know, so think of a pen and a pen cap. There's nothing stopping you from just rotating the pen cap if you're holding a pen. There's the point of connection is still there. You're not breaking anything, but single bonds you can rotate. Now, double bonds, they actually are rigid. So in this molecule, it's the one I showed you on two slides previous. We can take this half of the molecule and allow the bond to rotate, and that allows this CH3 group to actually change position. So these would be called conformers. They are not different molecules, uh, you know, because this rotation is happening all the time. Now, on the right, rotating around this double bond, because the double bond is rigid, actually gives you a different molecule. You could separate these two molecules, you could package them and sell them differently. You could get different, one might be harder to make and might cost a lot more. So the double bonds end up being rigid, and when both things attached to the double bond, like what I've got, a methyl group here and a methyl group there, both things are on the same side, we call it cis, and when the substituents, as we call them, are across from each other, we call it trans. Let's see. And this is very pertinent to people's health. You can have cis and trans fats. What I've got here is a part of a fat. It's not the whole fat. This is called a fatty acid. This is the trans version of it. This is the cis version of it. And if you want to make this into a fat or an oil, you pop off the hydrogen and you attach to this part of the this whole thing down here. 1 carbon, 2 carbon, 3 carbons. Each carbon has an oxygen. That's glycerin. And then each of those oxygens can hold one of the fatty acids. The examples I've shown are oleic acid. There's all sorts of slightly different structures. You can vary the chain length, like how many carbons you got in a row. You can vary the number of double bonds. Things you'll notice, though, the cis isomer has a kink in it. It wouldn't pack as regularly and as nicely as the trans isomer, right? So the cis isomers tend to be oils when you make fats out of them. They tend to be liquid. That's why we call them an oil. The trans ones would tend to stack up a bit better and solidify easier. Okay? The trans fats are not natural products. They're byproducts of hydrogenation. I've got a slide on that later. Basically the kinks in the cis fats are actually what makes them good for you. Now, a fat doesn't necessarily have to have a double bond in it at all, which gives it more in common with the trans fats and makes the substance have a higher melting point. It becomes a solid more easily. Okay, so basically I'd forgotten I had this slide in here. The R group here basically is whatever is attached, and basically you can see the R group way of clarification. Tag, I like that. The trans fats do not give me personally a higher shelf life. So so one thing I had mentioned earlier is that the electron density for the pairs of electrons in double bonds are very much more accessible, and I've shown you that model. The sigma bonds, as they're called, the electron density is just really in between the two atoms and is much less accessible. All right, well, where do these lobes of electron density come from? Um, I'm going to give just a very hand-wavy explanation of that. Um, you know, where electrons can be is governed by quantum mechanics. I'm not going to be subjecting you to math today, sorry. Tag. We can maybe do more math in a math club um, on quantum stuff. But today, I just want you to think about waves. Think about sitting by the edge of a pond and watching the ripples in the pond. Um, the ripples that you see in this slide, this is actually beautiful because you can see two sets of waves. Presumably, two stones have just been thrown in, and you can see um, the an interference pattern as the waves travel through each other. And in some places, you know, when the peaks of the waves are aligned, you get a bigger wave. That's called constructive interference. And then in other places where where a wave and a trough form, you know, overlap, basically cancels out to zero. So you get destructive interference. Yes, absolutely. So we can also think of vibrations on the string. I'm going to be using these slides on Monday for my freshman chemistry class because we are starting talking about this stuff. You know, a string has boundary points where it's clamped down. Electrons don't really have those boundary points, although the attraction to a nucleus represents a limit on the motion of the electron. String is one-dimensional, of course, and electrons are going to move in three-dimensional space. But let's think about what can happen on this string in one dimension. Okay? If you have vibration, you can have constructive interference of the vibrations on the string and destructive. So I've got two vibrations. One I put in red, one I put in blue, or vice versa. And then I just added up. This is just a sine wave. I just added them up. They're both plotted, but the blue is underneath the red, so you can't see. But when you add them up, you get purple. Okay? So basically, this would be like one phase of the string. At slightly later time, you might see the string kind of down in the bottom section. Okay. Okay. So we would call this like the fundamental. It's basically the lowest energy vibration that could happen in this string, and it only gets higher in energy from there. Right? Oh, that first slide was constructive interference, but if I drew the blue sine wave and the red sine wave as shown, you can see how interested Marty is in. If I draw the blue and red as shown, where the blue is positive, the red is negative, and when you add them up, they cancel out. Right? So this is what waves do. They have constructive interference and destructive interference. Okay. Let's see if this string were vibrating twice as fast, it would have an area where it's moving up while an area is moving down kind of on the other side of the string. There'd be a point in the middle that is motionless. That point is called a node. And again, you can have the constructive interference when you have two of these waves of this same frequency on the string, or like in the same pool of water, for example, if it's a water wave. And red and blue would make purple, and you get a bigger wave there. Okay. And you can think about this in two dimensions. Chladni plates are wonderful things, and I've got some links to them. Essentially, they're two-dimensional plates on some sort of shaker, and then you throw sand on them. And at the nodes, or the nodal lines, or the nodal planes, the sand will collect, allowing you to visualize like where the motion is happening. So these plates have vibrations happening, and you can kind of see the shape of the plate and the frequency of the vibration will determine like what shape these things have. Okay? So in one dimension, the waves along a line. In two dimensions, the waves along a plane. Which one? In three dimensions, that's what happened for the electrons. They're going to the waves are going to show up as three-dimensional. So yeah, basically here's some more cloudy plates. I happen to like the one with the violin. Kind of shows the shows how complicated the waves can be if you have a complicated medium that is supporting them. So for electrons in 3D, here's my hand-wavy explanation. I was able to find a public domain hand waving. I'm going to use that over and over again. So I mentioned that the attraction to a nucleus sets one boundary condition. The description of the wave comes from Schrodinger's equation. It's not the psi, not the actual mathematical representation of the wave itself that tells us what the electron's doing. It's the square of that. So what I've shown with the red and the blue in my models are the psi. That shows the phase, right, where you have maybe one part of the probability, or one part of psi as positive, one part of psi is negative, and it allows you to think about how putting those things together is going to lead to constructive or destructive interference. But after you put them together, you have to square the whole thing, and then all of the regions are positive, and that number is related to where the electron actually is. Okay? The math for this size just leads to really surprisingly simple patterns. Okay, and I may be oversimplified here. This is a generic atom. So right in the center here, there's going to be a nucleus, and where electrons can go are represented by each of the circles. And so these circles are organized into shells. So in our first shell, we've got a single, we'll call it a subshell, just one line. In our second shell, we've got two subshells. In our third shell, we've got three subshells. How many would our fourth shell have? Yeah, 4. Yeah. Okay. And there's an equation that gives us those numbers. I'm not going to inflict it on you. And in fact, if we're talking about second row elements, we're really just looking at what's happening in this second shell. If we're talking about hydrogen, we're really looking at what's happening in that first shell. Let me go into a tiny bit more detail on the shells. Each, if you kind of zoom in maybe to the shell, we look at the first shell. It's really got only one slot into which electrons can go, and 2 electrons can go in a slot. So in that first shell, you could put 2 electrons in. That's why hydrogen is happy with 2. The second shell contains a duplicate of what's in the first shell, plus something new. And the new thing has 3 levels in it. We're going to call them orbitals. where you can stash electrons. So with the 1 and the 3, that's a total of 4 column slots where you can put electrons. That's where our octet rule comes from. That's where that 8 electrons come from. I won't talk much about the third row. There's a whole thing in transition metal chemistry called an 18 electron rule. Notice how the third row or third shell has the stuff from the second shell, a 1 and a 3, but then there's a 5 as well. Right? 1 plus 3 plus 5 is 9, with 2 electrons each. That would give us 18, and for transition metal chemistry, you do find that there is an 18 electron rule. So in the fourth, we would have all the same as what's in the third, plus another, the trend is 1, 3, 5. The next in the fourth would be a 7. I'm not gonna inflict too much of that on you. So far, so good. Okay, moving along here. And as an aside, how this little diagram plays out actually predicts the periodic table's shape, as each row, as it fills up, corresponds to filling up different levels and sub-levels, right? And that maybe if I click on that up there, and okay, so if I click on my periodic table, it might decide. Oh, it's on the other side. Sorry, it's actually doing the periodic table on the other side. Well, that's annoying. We'll do a do-over. I'll flip it around. Okay, so now if I actually have the front facing you, if I click on this, let's see, new, and I'll just give you the normal one. There we go. And what we see is boxes corresponding to the elements, and each new box represents one more electron being put into the orbital diagram that we've got below. And those elements were that I alluded to that had the 7, the subshell that had 7 orbitals in it. Those are out front, and that's the way it's usually represented on a periodic table. But oops, let me click here and let's move. If you wanted to, you could represent the whole table where those elements are shoved in. Right, and then you have all these different neighborhoods of elements in the periodic. All right. Yeah, let's delete those as distracting. Okay, I'm going to move that back. Okay. Okay, so if you actually did the math, you can solve what the shapes of those orbitals look like. And for us, if we're talking organic chemistry, then we only need to worry about things that are spherical, like this one, and things that look like dumbbells, which are essentially these guys. They represent that second shell. That's pretty much where organic chemistry comes from. Right. So here's another representation. This is pictures from the orbitron, and you can kind of see a spherical region where electrons can be. You can see these dumbbell-shaped regions where electrons can be. And I like to draw the analogy to what's happening on a string. The dumbbell-shaped could be one phase versus the other phase, really kind of clearly maps nicely over what's happening. Okay. There's no reason why different shapes can't add up. So you had a wave looking like the red one and a wave looking like the blue one. You could get a wave, where you've got one big lobe and then one smaller lobe. We can do that with orbitals as well. So if we take our different shapes and we decided to mix them, because that's allowed actually in all of the math, what would happen is that we would get 4 new shapes, each with a big lobe and a small lobe, that point in different directions. And they actually point in the directions of a tetrahedron. So if we think of methane with our carbon atoms sitting in the middle, the lobes represent where the electrons can go off of the carbon, and each one could support a hydrogen sitting on the on the back. You don't have to mix all 4. You can mix 3, and if you mix 3, right, the spherical one, the dumbbell in the X direction, the dumbbell in the Y direction, well, you get 3 lobes, but they're confined to the XY plane. Right? The dumbbell along the Z axis is unaffected, and that's what I've drawn in gray here. And that's the origin of our pi bond. When we stash electron density in those unaffected, they're called p orbitals, but they're dumbbell shaped. When we stash electron density in the dumbbell shaped orbitals, it pokes out on either side of the atoms and gives us reactivity. 3 lobes would be planar, yeah. So these 3 lobes on this side are these lobes, and they are in a plane. And the last one, which was unaffected, is just above and below. Right. Okay. So this is where the bonding comes from. And I kind of, I've taken a long way around. I mentioned the methane up here where the hydrogens are bonding to each one of those lobes. And ethylene, where I showed you where we have the, what's it called? The sideways overlap of electron density. Okay. How about some fun stuff? I think reactivity. Consequences of the reactivity is actually really fun here. My cats were hugely interested in this morning. One thing that we talk about in a classic organic chemistry class is taking, here I've got 3 carbons in my, like a methyl group off of my double bond, so I can talk about something important. That electron density up in the pi bond can grab onto an H+, an acid, right? H+ is acid. And I've represented that in red. Essentially, that H+ would end up glommed onto one of the carbons. There are rules as to which carbon it would go to. It would actually go to the carbon on the left, because this methyl group releases a little bit of electron density, and that would stabilize where this positive charge ends up. Just, there's a region of electron density, or I'm sorry, there's an empty orbital sitting on this carbon. That's not going to last very long. Anything with a lone pair, like the chloride, for example, if we're adding HCl, would end up attaching to that second carbon. And I made a choice here. It could attack from the top. It could also just as easily as attack from the bottom. And the molecule that I've drawn here actually has, well, actually, it's not chiral. So in this particular case, it doesn't matter if you get attack from the top or the bottom. Um, but in some cases, attack from the top or the bottom would give you mirror images, mirror image molecules. And you know, if you're doing this to synthesize a drug, for example, sometimes the left-handed molecule is toxic and the right-handed molecule is not. So we have to be careful about that kind of structural thing. We got a couple of other reactions I want to show you while we still have a tiny bit of time. Okay, this is reversible, so you can go from the final product and turn it back into an alkene if you make the conditions correct. A lot of these things are reversible. Let's, in the interest of time, let me move forward a few slides. And yeah, talk about hydrogenation a little bit because I had mentioned cis and trans fats. So let's say that we have something with a double bond in it and it's cis, and we let it interact with a metal. This could be like a molecular metal compound, like just a molecule that's got a single metal, or it could be a surface, right? The area of electron density, that's the pi bond, could interact with the metal. If the metal also has a hydrogen atom nearby, that hydrogen atom can end up sliding like along the bond and ending up on a carbon. Now, that process is reversible, and notice how there's no double bond anymore. We have free rotation around these bonds, so the combination of the fact that there's free rotation around the bond and that the hydrogen can come back off means it doesn't have to be the same hydrogen coming off. It can be the other one. That would lead to some of the trans isomer. And, you know, if the molecule decided not to go, you know, back to the cis isomer or the trans isomer, you could get a second H. Say you are on a surface, hydrogen, like if it's a platinum surface, hydrogen can dissociate into hydrogen atoms on the surface and kind of just roam around. Another hydrogen could come in and break that bond, giving us our called hydrogenated product. You may have heard of hydrogenated soybean oil, like Crisco and stuff, where we're taking our cis fats, adding hydrogen to them, so there's no double bonds anymore. And that makes the molecules easier to stack together and makes them more liable to be solids. But in this process, we get small amounts of the trans fats forming, and that's has very poor health consequences. And again, I apologize. I have a hard time keeping up with the nearby chats. And I've got, as always, I always over prepare. I'm not going to inflict paracyclic reactions on you. What I did want to end up on was triple bonds. Bear with me for another 5 minutes here. Edit. And I've got that guy, and I've got that guy. You can make a molecule called acetylene. And acetylene is essentially just 2 carbon atoms, 2 hydrogen atoms. There's a triple bond there. Right? There's a pi bond in the XY plane and a pi bond in like the, let's see, I said XY. How about I call it XZ and YZ plane. I've given you the skeleton, so the white balls and the black balls all connected to each other. And I've given you a representation of both pi bonds. You can actually see there's a cylinder of electron density around this particular arrangement of atoms. These have a huge set of chemical reactions associated with them. One of the more interesting ones that I wanted to share with you, just move those out of the way, was as they've been explored if you have them in a row. Hello, click. If you have a bunch of these in a row, you might think, okay, well, that just means that I can share electron density like along a row in one dimension like a wire, right? So if we have what I've drawn here and move an electron in, and then we have a cascade of electrons moving around, so our single bonds, so our triple bonds end up just being an extended set of double bonds. We've essentially moved an electron from one side of this structure to another. This is the idea between having a molecular wire. Now, we are limited in how many carbons we can put together. It's about 10 in a row. It's kind of sad. If you had more that you could put together, and it be stable, then you'd have things that could be used truly as nanowires. The molecule I've pulled down, and it's just in front of the screen right now, is an example of something fairly exotic. It's got a set of 8 carbon atoms, 4 triple bonds in a row, and it's capped off by, let's see, these are platinums. And it turns out that you can take an electron away from one of the platinums, and you can watch how the electron hole ends up being delocalized between the two platinums. You can watch how it travels through this molecular wire. It's not totally straight. There's an orange bar going from platinum to platinum. That is the shortest straight line. You can kind of see that there's a bit of waviness to that. This is from an X-ray crystal structure from some of John Gladys's work from, I think, around 2005. One of the things that limits us being able to use molecular wires like this is the fact that if you just had, like, I don't know, say 1,000 carbon atoms in a row that are just triple bond, single bond, triple bond, it would be called polyacetylene. Polyacetylene reacts with itself, and it actually just gives you graphite. As all the double bonds rearrange, there's nothing protecting them from reacting with each other. The second type of molecular wire was from Claude Lapin's work. All right, and I'm bringing that one down now. And Claude Lapin and John Gladys are both inorganic chemists. And Lapin here has a longer, the red atoms are iron atoms, and there's a longer separation in between the iron atoms than there are in Gladys's work. And what he's found is that you can put conductive spacers in between some of these acetylene units to increase the length of these things being used as molecular wires. Now, sadly, the work on molecular wires is kind of superseded these days because we can do much the same stuff more easily and more engineeringly facile, I guess would be saying it, with graphene, with just single layers of single layers of carbon. Okay, and so that's where I wanted to end. A little late, sorry. And I really just wanted to talk about basic organic chemistry. Heavier elements can do pi bonding. Some caveats: they don't like to do it. Transition metal chemistry has a rich amount of pi bonding. In your biochemistry, there are double bonds everywhere. You know, I have a model up here of chlorophyll A, and I'll just show you that as the very last thing, just to show you. There is one double bond in this chain part, and then the green atom is magnesium in the little um, ring that holds the magnesium in place. There's lots of double bonds, right? Beta carotene would have been an example. If I'd had time, I would have made a beta carotene model. Um, I think it has like 10 double bonds in a row. You know, double bonds have so many properties. I didn't even touch on the absorbance properties, like what color they are, and the like. So that's where I am today. I wanted to thank everyone for their time, and thank NSF and all my colleagues, and you for your attention. You know, go through the nearby chat, see lots of comments. Thank you for always listening to me and being patient with me when I kind of get passionate about my chemistry. With that, I got some time for questions if anyone has any.
Mike, can you hear me?
I can.
This is Tagline. I have a question. My understanding is you can never have a pi bond without a sigma bond. And do you have any comments about that, and how I could understand that intuitively?
So for organic chemistry, I think that's true. There may be some exotic molecule in the inorganic world where that, may be the exception that proves the rule. So let's see. I think when we take our orbitals, I think when we take our like the s orbital and px, py, and pz, they always get mixed in some way, and so you can take a pair. You can take an s and a p, or you can take an s and a couple of p's, or you can take an s and all three p's. And when you do that, when you do that mixing process, you basically get an orbital that is pretty much designed to be to fill space in the cylinder around the two atoms that you're going to join. Our default, the most stable way of putting electrons and atom and nuclei together is if you have a plus charge, a minus charge right in between them, and then another plus charge. The minus charge in between the two plus charges would tend to draw those plus charges together. I think that being the most stable configuration means that it is required. When we get to our pi bonds, it's more like we're using a harmonic of where the electrons can go, and that harmonic has a node like where the sigma bond is. Does that make Does that make sense? Yeah. So I'm thinking that the sigma bonds are the lowest energy configurations of where the electrons can go, and they are the ones that get populated first, and then the pi bonds are the higher energy um, spaces where electrons can go. We have to have the pi bonds just to accommodate all of the electrons. Um, and because they're higher in energy, they end up being controlling the type of reactivity that's available. It is a stability thing.